Our world runs on data. From the artificial intelligence shaping our future to the simple act of streaming a movie, our hunger for information is insatiable, and the invisible infrastructure of the internet is groaning under the strain. For decades, the backbone of this digital world has been the humble optical fiber, a thread of glass carrying light across continents. But what if that thread could carry not just one signal but a whole rainbow of them? A revolutionary technology, born from both meticulous research and a stroke of scientific luck, is making this a reality. It's called the Rainbow Chip, a tiny device with the power to unleash a torrent of data and redefine internet speeds as we know them. In 2020, researchers in Australia used a single optical chip to achieve a speed of 44.2 terabits per second. To put that in perspective, that's fast enough to download over 1,000 high-definition movies in the blink of an eye. And they didn't do it in a pristine lab. They did it using the same type of fiber optic cables that are already in the ground all over the world. This isn't an incremental upgrade. It's a quantum leap. The device that made this possible is a fingernail-sized chip called an optical microcomb. It takes a single beam of laser light and, like a prism, splits it into a brilliant spectrum of hundreds of distinct, usable frequencies. Each of these colors can act as its own independent channel for data, multiplying the capacity of a single optical fiber by orders of magnitude. This Australian achievement was a deliberate push to break the limits of data transmission, but one of the most exciting breakthroughs in this field happened completely by accident. In 2025, a team at Columbia University, led by Professor Michael Lipson, was working to improve LiDAR systems, the laser-based eyes for self-driving cars. Their goal was to make brighter, more intense laser beams so cars could see further. Andres Gil Molina, a researcher on the team, described the moment of discovery. As they cranked up the power on their experimental chip, they noticed something strange. Instead of just a more powerful single-color laser beam, the chip started outputting a special type of light containing many different colors, all lined up in a perfect, orderly pattern like the teeth of a comb. They had accidentally created a high-power, high-quality frequency comb on a tiny chip. They had stumbled upon a new, highly efficient way to create one of the most sought-after tools in optical communications. Before this, generating such a powerful frequency comb required large, expensive, and power-hungry lab equipment. The Columbia team showed how to do it on a single, compact, and energy-efficient chip, solving a major piece of the puzzle. While Australia broke speed records, and Columbia had its happy accident, another piece of the puzzle was being solved in Sweden. At Chalmers University of Technology, a team led by Professor Peter Andriksson focused on amplifiers. As light travels through fiber, its signal weakens. Amplifiers are needed to boost it along the way. For decades, the standard amplifier has been limited in its bandwidth. In early 2025, Andriksson's team unveiled a new amplifier on a chip with 10 times the bandwidth of existing systems. This tenfold increase opens the door to transmitting far more data channels, more colors of the rainbow through a single fiber. So how does this tiny chip actually work? The magic behind the Rainbow Chip hinges on two concepts: wavelength division multiplexing, or WDM, and the optical frequency comb. Think of an optical fiber as a single-lane highway. In the early days, we could only send one car, or one wavelength of light, down that highway at a time. The amount of data was limited by how fast that one car could go. WDM, a technology developed in the 1990s, was the equivalent of opening up dozens of new lanes on this highway, each reserved for a different color of car or a different wavelength of light. At one end, a device combines all the different colored signals, and at the other end, a device separates them again. This allowed network operators to massively increase the capacity of their existing fiber networks without the insane cost of laying more cable. But traditional WDM has a big drawback. It requires a large number of separate, high-quality lasers, one for each color. This makes the systems bulky, complex, expensive, and power-hungry. This is where the Rainbow Chip, the optical microcomb, changes the game. It's a specialized light source that generates a whole spectrum of evenly spaced frequencies from a single laser. It acts like a master conductor, creating a perfectly synchronized orchestra of light waves from a single instrument. It effectively replaces a server rack full of 80 or more individual lasers with one tiny, integrated component. Inside the chip is a tiny ring-like structure called a microresonator. A single-frequency pump laser is shot into this ring. When the power hits a certain point, a non-linear process called the Kerr effect kicks in. In the simple terms, the intense light causes pairs of photons from the pump laser to convert into two new photons at different frequencies, one higher and one lower. These new frequencies then interact with each other, creating more and more new frequencies, cascading into a broad spectrum of perfectly spaced lines of light, a perfect frequency comb. The advantages are immense. First, miniaturization. An entire array of lasers is replaced by a single chip, dramatically reducing size and cost. Second, power efficiency. A single pump laser uses far less energy than dozens of individual lasers, which is a huge deal for massive data centers. And third, scalability. The comb structure allows for more densely packed channels, and researchers are constantly finding ways to create combs with more,